Okay, so let's take this example, and we're going to show that this example, L, the set of all of these column vectors, right, x, y, such that y is equal to 3x, is a vector space, or represents a vector space. Okay, so let's get started. Okay, we're going to use the usual meaning of plus and dot, right, addition and multiplication. So if we look at let's see here. So let's check condition 1. Now these operations are just the ordinary ones reused from subset L. Okay, so now right, so vector addition and scalar multiplication. Now, they're just ordinary ones as we would use with real numbers. And what we would say is that these operations are inherited from R2 in the two-dimensional reals. Okay, so now what we're going to do is we're going to do each one of these conditions. So we're going to do closure under addition. Okay, suppose that we have V1 is equal to X1, Y1, and we have V2 which is equal to X2, Y2. Okay? And these are all from the line L. Right? So this is two-dimensional space, so this represents a line. Right? And so we want the vectors that represent all of those conditions. So these two, V1 and V2, are both in L. And so if we add them, we're going to get X1, Y1 plus X2, Y2. And of course, when we do vector addition, we do component-wise addition. So it's just going to give us X1 plus X2, Y1 plus Y2. Now, we need to show that they're also that this resulting vector is also in L. So because y equals 3 times x, right? This is 3 times x1, and this is 3 times y2, or excuse me, x2. Well, it makes sense because I can rewrite this as x1 plus x2, and this will be 3 times the quantity x1 plus x2. So it is still in L. And for number 2, for the second condition, that addition of vectors commutes, we could just compare, right? So here's V1 plus V2, right? We got that. Now, it's easy to say, okay, well, these are just numbers, right? These are real numbers. So we can just, because commutative, the addition under normal addition is commutative with the real numbers. So I can just reduce these, right? I can just switch these. So if I do this and I just rewrite them, and I say that's the same as x2 plus x1 over y2 plus y1, well, I can then just split them apart into two vectors, and I get x2, y2 plus x1, y1, which is equal to v2 plus v1. And so I've demonstrated that the commutative property works for vectors in L. What else? Okay, let's do condition 3. Okay, so condition 3, the associativity of vector addition. So let's do this. Let's do oops. Okay, so here we go. Now what I'm going to do is I'm going to let's see here. Show this a number of different ways, but let's do it this way. So I'm going to combine these. So that's just going to give me x1 plus x2, y1 plus y2 plus x3, y3. Now the textbook might do it a little differently. So now I'm going to add these. So that's going to give me x1 plus x2 plus x3, right? Because I'm just bringing it in. So these are like grouped together. And so this will be x2 plus y2. No. Yeah. y1 plus y2 plus y3, right? Because these are already grouped together. So I can do that. So now what happens here? Well, I can use the associative property of real numbers here. So I can rewrite this as x1 plus x2 plus x3. And then I can write y1 plus the quantity y2 plus y3. And now I can split it up this way. And I can do x1, y1 plus the vector x2 plus x3, y2 plus y3. And of course I can then write it as x1, y1 plus x2, y2 plus x3, y3. And there you go. So that's condition 3. Now let's look at the fourth condition. And let's introduce the zero vector. So we have xy. Now the zero vector in this case would be 0, 0. And of course, if we add these, we just get x comma y. Because we just get x plus 0 and y plus 0, so we get the same thing out. So all we have to do is we have to prove a vector that acts as the zero element, and the vector of zero entries will do. Now note that the zero vector in L as its second component is triple its first. Right? 3 times 0 equals 0, right? 3 times 0 equals 0, so it works, okay? So this vector is in L. Now, let's talk about the additive inverse. So given any vector in L, right? So let's say for any vector in L, xy, is there another vector in V, in L, such that if I add those two together, I get the zero vector out? And yes, there is. Because what I could do is I could take the opposites of these, right? So I can take negative x and negative y. And notice that negative x, this is still in L, because if x is 3 times y, if it's negative, it's still 3 times y. And of course, if I add these component y's, I get the zero vector. So in other words, if I take V, well, the additive inverse is going to be negative V. And those are the first 5 conditions. So the first checks for the 5 conditions having to do with scalar multiplication are similar. Now for 6, closure under scalar multiplication, let's look at that. So remember, for scalar multiplication, you're multiplying the scalar by every component in the vector. So if we take vector equal to xy, such that it satisfies this condition, y equals 3x, then if we take r times v, that's going to be r times xy, which equals what? R times x and r times y. Now, let's rewrite this. We get r times x. X is 3 times y. Right? So now all I have to do is use the commutative property here for real numbers, and I can write this as 3 times r times y, and then we have ry, and we can see it still satisfies. This is 3 times that. Oh, hold on. Did this backwards. Y is 3 times x. This way. This is... There we go. So as you can see, it still satisfies the condition. And so the resulting vector is still inside L. So it is closed under scalar multiplication. Now, what about 7? Okay, so let's look at this. So let's say we have r plus s, two scalars, times the vector xy. Of course, what happens here? We can bring this inside, so this is going to be r plus s times x, and this is going to be r plus s times y. And then of course we could use the distributive property of real numbers inside, right? And so this becomes rx plus sx, ry plus sy, right? And now all we have to do is pull out the r and the s, right? Because now we can split this up, and so this is going to equal rx and ry plus sx and sy, which now we can pull out the r and s, so we get r times xy plus s times xy. And then for 8, we can do something similar. So let's take two vectors. And what we can do is distribute right? So, but we could do it this way. We could do it R times, now we can combine these. This will be x1 plus x2 over y1 plus y2, which is then going to equal R, how do I want to do that? Yeah, so R times x1 plus x2, R times y1 plus y2, and of course now we can use the distributive property for real numbers, and that's going to give us R times x1 plus R times x2 and R times y1 plus R times y2. And now we can split it up, right? So let's split it up into two vectors. We got Rx1 and Ry1 plus Rx2 and Ry2. And now we can pull out the R's, and we get R times the vector x1, y1 plus R times the vector x2, y2. And we're done. Okay, the ninth condition. Okay, there's a lot of conditions here, but we have to check them all in order to show that this is a vector space. Okay, so now we're going to do the associative property for scalars, right? So here's what we're going to do. We're going to do Rs times xy. Okay? So let's do this again. We're just going to bring it in and then use the properties, the associative property for real numbers. So we're going to do this component-wise, right? Scalar multiplication. So it's going to be Rs x, Rs y. And now we're going to use the associative property inside. So that's just going to be R times Sx, R times Sy. And now, what do I get? So if I pull the R out, well, what is it? I get R times Sx, Sy. And then I can write this as R times S times the vector xy, like so. And we're done with that one. Now, the final and 10th condition, and that's the multiplicative identity, 1. Okay, so now this is pretty straightforward. So the 10th condition, the final condition, we take the number 1, right? And we multiply it by any vector in L. And what do we get? Well, it's going to give us the same thing because, again, we're just going to do it component-wise, right? So bring the 1 in, scalar multiplication, we get 1 times x, 1 times y, and of course, inside there, it's just real numbers. So 1 times x is x, and 1 times y is y, and so we get the same thing out, and we're done. And so in this example, L turns out to be a vector space.